Hello, YouTube. How's it going? This is Carrie Sundra of Alpenglow Industries, and we are here for our 12th solder sesh. And tonight we have awesome guests. We have Lenore Edman of Evil Mad Scientist, and she is a founder of Evil Mad Scientist. And we're going to be putting together their 741 kit that you can see here on the desk in exploded view. We have cheated a little bit because it's like a little bit of a large kit. So we have pre-populated. Robin actually did all the soldering on this. So we've put on the 3904 transistors already, but we'll be soldering up the rest of the kit while we talk to her and ask her all about it. And then we also have Leborg here. And Leborg has been working with me for a little while now, and they're here to keep the conversation going and yeah, ask questions and stuff like that. So, and of course, Robin is also behind the scenes over here. So yeah. Oh, interesting. No audio yet. Is that fixed at all? Hello, Bob, by the way. Good to see you. We can all hear each other. Yeah, if anybody wants to comment, if you can hear audio or not, that would be great. Just so we don't get too far ahead of ourselves if it's a problem on our end. But hopefully it's not. All right, Brittany. Hello, Brittany. How's it going? Thanks for joining. Brittany is an in real life friend of mine. Woohoo! Yay! Geek Mom Projects. Deborah hears us. Awesome. Hi, everybody. It's awesome that you guys are all here. Cool. All right. Well, I will hand it over to Lenore now. I would love to hear basically the story behind creating this kit, like this one and the exploded 555. So we have that one here as well. I mean, the thing that I think is so cool about these is that like you actually get to put together an IC like by yourself, by hand. You get to see all of the components that are in it. You even get to like probe around and see how it works as it's working if you want to. So that's what I like about these kits, and that's why I think that they're cool and like awesome for learning, and just also just awesome fun things to just like have around and show people too. But yeah.
Okay, so the 555 kit is where it started, really. And of course, the 555 is a favorite of just about everybody. Leborg, you made the 555 pins that are awesome.
Yes.
So it's iconic. One of our 555 projects, let's see if I can get it here, is this 555 footstool.
Oh my god!
Oh my god! I love that thing.
Made out of CNC cut plywood. It's sturdy. It's great. So this was our 555 project that we took to an event called Analog Aficionados.
So should we just do a little introduction for people who might not know what a 555 is? About what is that chip anyway?
So the 555 timer is a ubiquitous chip. It's in almost everything. It's a timer. So anything that has blinks, that needs something to happen on a schedule, that makes tones, all kinds of things, the 555 is in. It's in your washing machine. It's in your toaster. It's in your car. It gets embedded into other chips. It's one of the most produced chips of all time. And like I said, it's just in everything. Yeah. And it was designed by Hans Kamensend in, I think, 1979. And since then, it's just been used in so many different things.
And it was really like the first way that you could make, basically with like a single chip and minimal surrounding circuitry, like a train of pulses, like a clock train or something like that, something that could be used to keep time, right? With like microprocessors, or like, as you said, blinking things, whatever. So it was like the first of its kind too.
It was one of the early ICs. Yeah. They were just starting to make circuits that did a thing, that you were putting together more than just gates and so on. That it was really used in so many different things.
Yeah.
Okay, so
I also feel like it's a really cool chip for beginners to like really understand ICs, because like it was the first IC project that I did. You first make the light blink, and then you make that like light theremin circuit, and you're like, oh, I kind of like get what an IC is doing, and it's not just some computer stuff, you know. So
Right, it's not a microcontroller where it's hidden in the code, or there's software part of it. It really is electronics. It's really you're using the circuit to create something rather than taking it out to another level of abstraction. So yeah, there's tons of kits that are built around it. Like there's the Drawdio kit where you make a musical pencil and just all kinds of things. Okay,
Cool.
so we made the footstool, and a friend of ours also brought a 555 project to the Analog Aficionados event, and he brought this. So this is made by Eric Schlepfer. He goes by Tube Time, and this is the 555 circuit on a breadboard, a traditional breadboard, an actual wooden board, and it's all of those transistors and resistors. That's all that it's built up of. And he set this down on top of our footstool. And we're like, oh, we have to do something.
That is awesome.
So we made the 555 kit. So you're talking about blinker circuits. So I've got an example here. This is one of our 555 kits set up with. I'm going to hook up my 9-volt battery here, and this is just an LED blinker circuit.
Nice.
So yeah, just a couple of resistors, a capacitor, and a power source. So yeah, it's one of those things you can make something that does something with very few components. So after we made the 555, people loved it, and we're like, oh, what are you going to make next? And we made the 555 with these cool decorative legs, the stand for it that look like IC legs. We wanted to keep in this form factor, the DIP 8 form factor. And so other popular chips that come in a DIP 8, and DIP is dual inline package, so your standard through-hole chip package.
Yep, two rows of legs.
So that the 741 was another obvious one, in part because, again, it gets used in a lot of things. It was one of the early op amps. It was the first op amp to include a capacitor inside. So that took up a lot of die space. Capacitors take up a lot of area. So it was one of the early ones. So that's how it came about. So we've got that.
Cool.
So you can see the capacitor on board. It's a little different. It's a little different ratio when it's discrete components.
Yes. I was surprised that this only had one capacitor in it. Yes. I don't know. I just assumed that there would be more. But
you would need so much more die space.
Yeah. And I don't know if that. I mean, things are always getting smaller, and they're always coming up with new materials and new ways of doing things. But I wonder, are capacitors on dies a lot smaller now than they were in the 1970s, or is that just some laws of physics that you can't really get around and they still take up a lot of space?
I think it's laws of physics, and we tend to just use discrete capacitors for the most part now. If you're interested, I think that Ken Sheriff did a die photo and article on the 741, so you can see how much of the die the cap takes up.
Cool.
Cool. Really cool. He also did one for the 555, which is just fun as well.
Nice. I didn't know that people hide artwork on dies, on integrated circuit dies. So
that's one of my favorites. That's one of my favorite like electronic secrets to have ever discovered. It's so like whimsical and fun.
Yes. Yeah. So dies are the things that go inside. Are the substrate that your entire circuit is printed on, that are microscopic, that are inside of these, black bodies that make up our ICs. So that's what we're talking about when we're talking about dyes.
Although,
and so on microscopic levels, people put like little fun action figures and artwork and weird stuff on there. So it's lurking in all of your electronics without you even knowing about it.
Yeah, there's some famous ones that have like a pair of scissors. There's signatures. There's all kinds of stuff in dice. So we call these our disintegrated circuits because they're integrated circuits that you blow up and take apart and make from discrete components. But one of the things that we realized is that it would be fun to do an intro surface mount version of them so that people could get started with surface mount soldering or just for fun. And so here's the 555 version of that. And one of the fun things that we did with this is we made it to scale. So you've got your dip 8 and your SOIC.
Nice.
So
nice. Hey, Robin, could you look in our ICs bin and see if I think we definitely have some actual 555s in there. And just like pull a few out so that we can show people like what the actual size of these chips are in comparison.
They're like
I should have had that ready ahead of time, but I did.
So, and then we have the 741 too.
Yay! Nice. I definitely want to collect the surface mount ones too. Those are super cool.
Yeah, these ones are fun. We did the black substrate with a clear mask on these so that you can see the copper layer.
Yeah,
nice.
Very cool.
Great.
Very, very cool. Yeah, so meanwhile, the soldering that I'm doing is like relatively simple. I'm just taking these resistors and bending their legs, and the kit has very, very nice instructions, and the resistors are laid out in this very nice card. Which are these things that you're getting custom made? Like, I have so many questions about this card. I saw this and I was like, oh dang, I need to like up my kit game here because this is like next level.
Yeah, we have those cards die punched for us and stuffed, shipped to us stuffed. Although we do a few kits that are super low volume that we use those cards for, and we stuff in-house.
Yeah, so it's really nice, and they're like the other nice thing that you don't often find when you have kits of resistors is that so not only are the labels next to them all here, but the legs are tucked in underneath the labels so that they don't fall out. So they're all stuck to the card, which is super nice. So yeah, nice.
The cards are inspired by needle kits. You can buy sewing needles in packets where the needles are put through like a piece of fabric, and they're usually arrayed by size. So that's kind of what they're inspired by, is sewing kits.
Nice. Yeah, that makes sense. That makes a lot of sense. Cool. And right now I am putting in the 51K resistors, 51 kilo ohms. So it's 51,000 ohms. Not to be confused with the 51 ohm resistors. So, yes. So making sure I put them in the right holes.
One of the reasons that we use the card is that it's really helpful to have it clearly identified which is which. Do you use a resistor lead forming tool?
I don't. The kits that we've sent out so far, we've basically used resistors that are on cut tape. So we just cut the number of resistors that we need out of the tape so that they're held together. I have one of those for when I'm doing stuff. I don't know why I tend to only use it when I have like a weird size, basically, that I can't. That's a little more difficult than just sort of bending both the leads right at the resistor.
Sure. We like it. It always comes out tidy when you do it. So this is a resistor lead forming tool. Now the question is, do I have a resistor? Gosh. Probably. But essentially, it is a guide for you to put the resistor in and bend the leads over the edge. Yeah.
Nice. So we have a few questions here, and hello everybody who joined. Hello Jason, hello Brent, hello Dan. So question we have is, a few actually. We have what is over your shoulder, Lee? And we also have what, oh wait, which shoulder? Oh yes, we have two L's, David. That is so well, I think the thing over Lee's shoulder is cool too. We have what's over Lenore's shoulder.
Probably
too.
not the question though.
And we have what size components do you use on the SMD versions of your disintegrated circuits?
So we wanted the surface mount ones to be usable, so solderable by humans. So there's a 1206 resistors, and I don't remember the name of the size for the transistors off the top of my head, but they're a fairly large scale one, so that they're doable by humans with a soldering iron. Or a skillet or reflow, whatever your preferred method is. But we didn't want to go with something so tiny that you can't move it around yourself.
Yes.
I mean, we've done that LED challenge, and
it's fun, but it's a whole other thing.
Right.
Yeah, I draw the line at 402s, and I definitely need magnification for those, and I'm not as good at them as I used to be.
Yeah, I have not done much surface mount soldering. Just haven't had too many opportunities to do so, and big components are much easier for my middle-aged eyes.
Yes, magnification is such my friend. Such my friend.
So I think the question is about what's over my shoulder here.
Yes.
Yeah. And so this is part of the story. Once you start making disintegrated circuits, people start asking you questions like, well, what if you wanted to make a processor? Could you do that? And the answer was, well, let's think about what that would take and maybe do some proof of principle work. And oh gosh, you actually can. And so this is a recreation of the 6502 processor of individual transistors. So let me plug it in. There we go. All right. So
whoa.
A processor on its own is not very fun to look at. You can't see what's happening inside, so we added LEDs.
Excellent.
So there's all the green LEDs down here. That's the registers. There's LEDs indicating some of the other things that are happening as it's running its program. And so you can make a processor out of discrete components. It turns out, if you have a lot of dedication and are willing to take a dare like that. This is also Eric Schlepfer's work primarily. We've been working with him on it for years to bring it to prototype stage, and eventually, hopefully, we'll make it possible for other people to get some. But we'll probably have to wait until the chip shortages and things iron themselves out and the supply chains are a little bit more dependable.
Yes, that's been a big bummer for all of us. So how big is that actual circuit board?
It's about 12 by 14. It's essentially a panel. So we're here.
Oh wow.
Nice. Well, you have a lot of love on these in the comments. I mean, yes, LEDs improve everything. Geek Mom Project says absolutely, and I Shot JR David says this is the most impressive thing he's ever seen in his life. Sorry, childbirth. Dang. And yeah, Deborah says if the chip shortages keep going on, we may all need to know a lot more about 555 because we'll just be building everything out of them. That is the truth. Wow, Cool.
So the 6502 is a processor,
Yeah.
and in order to run a program on it, you need supporting hardware. You need all of the the timer, the clock, and so we have an ARM on here that does all of the supporting hardware for it. Is emulated.
That's hilarious. You have this like high-powered processor that's doing the support work for those little.
In theory, we could also emulate the 6502 itself.
Mm-hmm. That's pretty awesome. So the 6502, I'm not super familiar with its history. I mean, I kind of recognize it as being like an early sort of bare bones processor, but what are the types of things that people built with it?
So it's most famous for things like Nintendo, the Apple II, the Apple One as well, I believe. And a bunch of other. So the thing is that it was low cost. It was bare bones. It was easy to program around, and so it got built into a ton of things, Commodore stuff, and just. And then the chip itself got used as a processor embedded into other types of hardware as well. So it just would get plopped onto a project on its own. So it's in a lot of things, and a lot of people, the first time that they learned assembly, learned on the 6502. So it's also used in education now as a way to learn assembly, because it's small enough that you can wrap your head around everything that the chip does. And that's not true with modern processors that have so much capability. So it's used as an educational tool, in part because it's limited, that you can really understand what's going on.
Yeah, that makes a lot of sense. I did not take higher level electronics courses in college, and so I never had to learn assembly. And I would really like to do some assembly work, because I think it'll just sort of round out and better my understanding of memory management that's going on in processors, because that's something that you don't like, especially for small processors, because you don't need a full computer. You don't need like a Raspberry Pi to do a lot of very simple things, even just to like run servos, or to blink lights, or to like read a temperature sensor or something like that. You don't need a fancy processor to do that. That's running an operating system and, has input capabilities, right? You just need like a little chip that you solder in that does its little job over and over again really well. And so, so with those chips, like memory management becomes a big deal, because they have very limited amounts of memory. So you have to be careful about how big of numbers you're storing and things like that. Like if you have a number that's only going to vary between like 0 and 100, you'll store it as like a smaller 8-bit number, rather than having a number that, like, let's say has some decimal points and, can practically go up to infinity, which you will store as like a larger, 4-byte number. So yeah, you have to start thinking about that kind of stuff with like low level processors. And but even so, even with the Arduino environment, like a lot of that stuff is sort of hidden under the hood, and you don't really have to worry about that in order to program it. So, but there comes a point in time when you're like, well, I want to worry about that. I want to know how that works, and maybe I want to use even like smaller, cheaper processors, like the At-Tiny4, for instance, which I'm like poking around with right now. So, yeah, I'd really like to pick up some assembly skills.
It was interesting that you said you didn't take any higher level electronics courses in college. Yeah. I didn't take any electronics courses in college. My degree is in interdisciplinary studies, English and Greek.
Of course it is.
So I have learned electronics just by doing and by supporting. We've been making a lot of electronic kits since 2007. making and selling. Yeah, the business started in 2007. And you get to know circuits really well when you're helping someone figure out what they did wrong in soldering it.
Yeah.
And so it's sort of that if you have to teach something, you learn it better. But if you have to support it because someone built it wrong, you learn it even faster and even better.
So what were some like early like lessons learned from building these kits and having people solder them wrong and things like that? Were there things that surprised you that you then like changed and iterated on or had to like come up with a way of explaining better or dealing with?
So we've always put a huge level of importance on documentation from day one. We do when we see someone making or more people making the same mistake, then we look at our documentation and find out how we can make that more clear. Because if you are seeing the same mistake over and over, there's something that people are missing. And so we watch for those kinds of things. They don't happen as often now because we've been doing it for a long time, and we can reuse a lot of that knowledge that we've gained. So it's been a while since I've noticed something like that. But yeah, listening to the feedback you get and what kinds of problems people have and so on. And then just like general experience, we have employees who have been colorblind, and then you have to really think, okay, if I'm going to have a soldering kit that has through-hole resistors with colors on it, I need to make that clear even without referring to the colors, what they are. So that's, like with the card, having them marked and so on. And that makes it easier to move into things like surface mount that don't have those kinds of colors, because you've already gotten used to explaining things in a way that don't refer to those types of characteristics that are, more fundamental.
Yeah. No, that makes a lot of sense. Yeah, I regularly get teased by a few really old friends about not knowing off the top of my head the resistor color code.
Oh, I don't know it.
And I'm just like, dude, you can't even see the colors anyway. Who's like, especially if it's on a blue background, how can you tell red from brown? Like, you can't. So yeah, I feel like it's good to have alternate ways and to be able to like use a multimeter and things like that.
Right.
So, we got a lot of good comments. I'm behind on them. So yeah, Atari 2600 was another thing that
I will say the list of computers that run on the 6502 is really, really long. And if you stand with the monster 6502 at like a Maker Faire or a Vintage Computing Festival for any number of hours, you will have someone come up and tell you about the computer that they used with the 6502, which is not on the list that you had previously. It will happen. So I will never say a comprehensive list of computers that were made with the 6502 because it's really, really long.
Yeah. Tamagotchi was also brought up. That's a good one. Yeah. And then a few recommendations for learning assembly on other processors as well. The 68,000 or 8386 are good learning paths, and people are talking about those different ones too. So cool. This is a good question from Geek Mom Projects. She says, these days, do you find that people will actually read your documentation, or do you find a lot of people asking for video?
Yeah, we get a lot of people asking for video. People have become accustomed to there being video for everything. And video takes so much more time to produce in a way that is useful than written and photographed images and so on. So we primarily do written documentation. With lots and lots of image heavy written documentation. We will occasionally do a video when it's clear that it's something that will be helpful for instance, with our pen plotters, there's a few things where we get some questions that are a little bit hard to describe. I'll say they're easy to describe. They're hard for people to read our descriptions, depending on how you learn. So there's a few things that we do video, but for the most part, we do written stuff. And I would like to do more video. There's just not enough hours in the day.
Yes. And the other thing is that written documentation is way easier to change and to add to than video is. So you can, I feel like written documentation, you can keep fresher and adjust a lot easier.
You can iterate it. Yeah. Video is much, much harder to do that with.
Yeah. So tell us a little bit about the pen plotter and about the eggbot too, because those are super cool things that you guys make. And
so the eggbot was our first pen plotter, pen plotter that draws on spherical and egg-shaped things. That was a collaboration with Bruce Shapiro of the Art of Motion Control. So he's a motion control artist, and wanted to bring it out to a wider audience, but didn't want to do kit production. And so we worked with him to get it manufacturable and supportable. So one of the challenges with things like the pen plotters is that you have to support software, and it needs to work on people's computers that aren't yours.
Yes.
So basically impossible.
So the eggbot works on with an extension for Inkscape, the vector art program.
Yeah.
And
okay, cool.
So we've been working with Inkscape. The eggbot came out in 2010. So we've been working with Inkscape for a really long time now. And the next pen plotter that we made was the watercolor bot, which was a collaboration with our friend Zeph, who wanted to compete in a robotics competition in the art bot category. And so we helped Zeph create the watercolor bot, which was a lot of fun. And it was such a great experience that we wanted to get it out to more people. So we worked together to get that out. It's not currently in production. It turns out there's not a huge market for low precision watercolor robots, but it was very fun.
Yeah, I feel like that's totally part of its charm. That's why I love it. I'm like a huge fan of low precision robots. They've got like expression, but I see why.
Okay, so the watercolor bot inspired Lindsay, our friend, to create the first version of the AxiDraw. And this is again he didn't want to go into production, so we took the project over and redesigned it again for manufacturability and supportability, and that came out 2016 maybe. Mm-hmm. And so we started making it, and we're absolutely inundated with orders. I had no idea that that people needed pen plotters.
What are they using them for?
Okay, so my favorite, and what you will see a lot of in the right places of the internet, is the algorithmic artists. So hashtag plotter Twitter.
Plotter Twitter is beautiful.
Plotter Twitter. Okay.
Oh yeah,
nice.
I
need to look at
love
this.
Plotter Twitter. There's so much beauty there.
So
there are
good.
even people using AxiDraw with watercolors. There's Alicia Hay, I believe, does some amazing work. I've seen some people doing other kinds of paint things with AxiDraw as well. But Plotter Twitter is just fantastic. So that's my favorite, is the algorithmic art community. Nice. But the most popular use for it is handwriting like applications for marketing purposes.
Oh, I hadn't even considered that. In my head, it was all Plotter Twitter. It's just my art brain. I'm like, yeah, for sure. It's just robots drawn stuff.
That is so interesting to me that that people are using it for that kind of marketing application. Like I'm I'm curious as to like, okay, so why wouldn't you just make something on like using an iPad and, you know, whatever artistic software you like, and then print it? What is different about like the ink plotter? What kind of like feel does it give rather than sort of a more traditional like printing process?
Well, if an envelope comes to you that is addressed that was written with a pen versus one that is ink jetted with a handwriting like font, which one are you more likely to open?
Yep.
Or you are ordering something from an online company for the first time, and they want your loyalty, and they include a handwritten note in the package thanking you for your order.
So basically, we need to stop handwriting our notes and get one of these plotters because, get a robot to do it for us, because this is...
Can they hold sparkle pens?
Yeah,
Yes.
can they hold sparkle pens? That is very, very important here at Alpenglow Industries.
There's a Discord for the plotter community. I'll think of the name in a minute. Anyway, lots of discussions about pens, and specifically gel pens, and also more specifically glitter gel pens. Also the color changing gel pens. All of the yes.
Awesome. That is rad.
I'm just about to put a UV pen in my plotter, so yeah, I'm like all about this.
Yeah, I love the stuff that people do with UV stuff, or the writing on glow in the dark materials with a laser, so that you have temporary artwork that fades. Those kinds of things are really cool.
Cool. So I wanted to show you. So I just got done soldering everything, I think. Yay. I hope. Yay. I don't think I have any extra components, which is good. And so just a quick little break here. Thank you so much, Robin, for grabbing these out. If you could see if there's any questions that I've missed, that would be cool too. So here we have back to the 555 timer chip. This is an actual 555 chip next to it. And this is like an old school through hole one that you might use. Here we can do like a little switch to microscope view here real quick. So that's our actual 555 timer chip. Between the legs is about 1/10 of an inch each. So if you need an idea for scale, it's like about like 4/10 of an inch long, about half, like a little under half an inch maybe.
The spacing between the legs should be 0.3 as well, between the two sides, two rows.
Oh, between two sides. Yep, is 0.3. Yeah, 0.3 inches. So that's kind of how big this guy is. And then the surface mount version is even smaller and tinier. It's about like 1/4 of the size, I would say. I don't know the pitch spacing offhand for that one, that's but right. Yeah, that's like a large. Yep. And even to scale, that's awesome. Nice work on that. But yeah, like that's a large chip these days. Like other chips, I think the 555, I think it still requires relatively big die space, so it doesn't come very much smaller than an SO8 here, I don't think, at least not that I've seen. But you can get chips that have just as many legs that are 1/4 the size of this now, even. So it's kind of crazy. And so like back to showing them all on one. Right?
Nice. Yeah.
What we're talking about. So it's like it's really useful to have something this big so that you can see what's going on inside of it.
The other fun thing is if you blow something out, you can trace and figure out what failed, and then you can replace it.
Nice. That is an excellent point that I had never thought of. Very cool. Yeah.
Okay, so here's the size comparison. Here's the 6502 in the 40 pin dip package
yeah.
with a 0.6 inch pitch. So
Nice. Yeah.
there.
Yep. much bigger. Cool. So let's see. Now we've got to put on the legs. These are super cool. And now I feel like with the 555 there was something about like, I don't know, there was something about spacing them if I remember. Oh, that's right. There were spacers between the bottom and the legs.
Yep, you should have some
Yes.
some black
Cool.
washers for that, nylon washers.
Yeah.
And
'Cause I think I forgot to put them in first and then had like extra parts. That's why like that stuck in my mind. And I was like, oh, I see what these are for. Yeah. So that your legs don't don't like accidentally short anything out.
and they
there.
shouldn't, since they're anodized, they shouldn't be electrically conductive, but you still want to space them just in case.
Oh,
and
cool.
then-
So these are clear anodized.
Mm-hmm.
Nice.
And then the screws that you're using there are thread forming screws. So the legs themselves aren't tapped. You're just forming threads with the screws.
Oh, interesting. They kind of look like they have slight impressions of threads in them. Oh, in the actual legs.
In the
Got it,
actual
got it,
legs,
got it.
the screws that
Not
you
the-
use,
yeah, not
the little black ones there that you're going to attach the legs
Cool.
with. Yeah.
Yeah. Nice. Awesome. All right.
I love that they're called trilobular. Yes, they have a
Trilobular.
wonderful
Yes.
shape to them. Trilobular thread forming screws.
Oh, I need to pay attention to the colors. I should read the instructions.
Yeah, because the 741 has a really weirdo pinout that dates back to when it was in a can shaped package.
Oh, yeah.
With where is your power and your ground? They're essentially opposite each other if you're in a can, but not so much in a dip 8. And then the active pins are in sort of strange places.
Yeah, like usually you would think that either opposite corners would be power and ground, or both the
Yeah,
top
so
would
with
be
the-
power and ground.
With the 5x5, it's pin 1 and pin 8.
Yeah.
Yeah.
Yep. But yeah, here they're like 4 and 7. Cool. So we have a question in the comments of what is an op amp?
So
Which
op
is-
amp stands for operational amplifier.
Yeah.
So it's used for amplifying a signal or a voltage or I don't know what. Here's the thing. I've only used op amps a little bit, but I make a lot of them. So so I'll let you go into the technical details.
Yeah, I would say that like the another reason that op amps are kind of cool is that they can do more than just amplify. So yeah, hopefully we'll see what our time is, although we're doing pretty good on time. Wow. Got that soldered under an hour. Dang. Nice. Thanks for giving us the head start, Robin. That was awesome. So yes, they can amplify signals. And like, what do we mean by that? Well, like if you think about the volume knob on an old stereo, the volume knob is actually just a variable resistor. And that is hooked up like to your audio signal and also to something like this op amp. And so it actually makes your audio signal grow and shrink as you twist that knob. And so that's what we mean when we're talking about amplifying. And so, and then your amplitude of your audio signal is what correlates to volume. So they can do a bunch of stuff like that. And there were a lot of old sensors, old analog sensors, although they weren't old when I started into electronics. It was like the way things worked. that basically they changed resistance with respect to some sort of input. So some things change resistance when the temperature changes. Some things change resistance when pressure changes. And so you basically took these little, resistor bridges, and what you could do is you could power them, and then you could see a tiny difference in signal that was made by that resistance change, and then you would put them through this amplifier so that you would be able to like look at the range that you wanted to, and be able to get a lot better resolution in that range. So instead of just being able to differentiate, like, I don't know, like boiling and freezing, right? If you then amplified that signal, then you could be like, oh, this is 75 degrees and this is 80 degrees, that kind of thing. So amplifiers were used a lot in instrumentation, and there are like specific kinds of amplifiers that are made of usually like maybe 3 op amps that are called instrumentation amps, that are used for that kind of signal processing. And now I think it's like pretty much all sensors are now digital, so they just like spit out a bunch of ones and zeros that correlate to your temperature or your pressure or whatever, but they still have all of this stuff internally in their ICs. So it's still like definitely useful to understand how they work. Another cool thing that they can do that's like not amplification is they can be used to compare two signals. So like, is this signal bigger than the other one? And if the answer is yes, then I output like 5 volts. If the answer is no, then I output 0 volts. So it was a very early way of kind of creating something that was digital signal friendly, that was only either at 0 volts or 5 volts, that a little processor or computer could actually read and do something with, versus having this signal that like changed like kind of in infinite increments between 0 and 5 volts. And I think that A to D converters are like, so converting an analog signal that has like a bunch of, that has basically infinite variation between 0 and 5 volts, converting that to a digital signal that a microprocessor can like understand and store and read. I mean, I think that that's still done with like capacitors and op amps. And, it's like, okay, is this signal, bigger than 2.5 volts? Yes. Okay. Then we'll see if it's bigger than like 3.75 volts. Yes. Okay. Then we'll go. And so there's like this successive, that's how like SAR, ADC, A to D converters work. Successive approximation. I forget what the R means, but that's okay. But so that's an interesting use of op amps to be, and that's called a comparator because they're just comparing two things. And then you can also use them to not necessarily amplify, but like offset a signal. So if you have a signal that's let's say an audio signal that's like going through ground, it's like varying between positive and negative voltage, but you need to interface that to something that needs to read a signal that's like between 0 and 5 volts, and it can't really see anything below 0 volts. Then you can like use an op amp to offset that signal. So now it's going between like 0 and 5 volts instead of positive 2.5 and negative 2.5 volts, let's say. So like, yeah, useful in a lot of signal processing kind of things.
So one of our first set of kits that we made were for interactive LED projects. And we made one that was entirely analog. So it was op amps and resistors and capacitors. And it would create a damped oscillation. So when you got a signal that changed a value from your photo transistor, then it would trigger the oscillation, which would then dampen out. But it will also send a signal to its neighbor, who would get a smaller signal and would also oscillate, but at a lower amount. So it was sort of a networked analog computer that would just sort of ripple in the amount of light that it had. So nice. It was a lot of fun. But occasionally people would say things like, would you please make sure that the chips are programmed? And it was like, well,
there's no.
these are just op amps.
That's funny. It sounds more like they had bad experiences with other kits, right?
Fascinating, yeah. Or they would say, can you change the program on those chips? It's like, well, in
Not
theory,
really.
you could put different resistor values and it would do something slightly different. Different capacitors, different resistors. But no, there's actually no programming involved.
Lenore, I'm kind of wondering,
I'm totally
like,
messing up these spacers. Okay, I see what my problem is.
Oh yes, the spacers go on the other screws.
Yes, on the other ones. Yes.
Feed the screw through from the top, and then put the spacer on, and then the legs. Yep.
That makes more sense. I'm like, this isn't working. What is going on here? What am I doing wrong? Talking and not reading. That's okay. That's how we roll over here on the live stream.
We do sometimes tell people who buy our kits, who are like friends of ours, you should actually read the instructions on this one, because there's actually some information that might be useful to you, even though you've made a lot of kits.
Nice.
Oh.
Let's see.
Lieborg, you were going to ask something.
Oh yeah, I was going to ask you. I had no idea your background was not technical. I just make random assumptions. So I was kind of wondering, was there a project that you were involved in or did or saw even that like really made you fall in love with electronics, like something that like really captivated you about it?
Electronics specifically? That's a really good question. The first sort of electronics-like projects that we did were LED projects, stuff to light up our bikes when we were dressing them up for events,
Nice.
and so on. So that was much more about display than about electronics themselves.
That's okay. I mean, I think that's a
That
good.
totally qualifies.
Yeah.
For sure.
Right?
And then so the other like super inspirational project from a different direction was seeing Bathsheba Grossman's sculptures at Maker Faire. Sorry, I don't know if you're familiar with her work.
No,
I don't think so.
Tell us
So
about
she is a sculptor who works primarily in 3D printing. And if you'll hang on for just a sec, I'll grab a piece.
Yeah.
Ooh, yeah, absolutely.
Totally. It had me thinking about like when I was in school and I took like this class called like electronics for artists, and we had to make it was to make a switch. We could make a switch out of like anything conductive. I still make my students do this, and I had no idea what I was going to do, and I ended up making a switch out of a pineapple, and you like put like the head of the pineapple on, and the LED would turn on, and I was like, whoa, electronics can be anything. And I think of like that as my origin moment, so I'm just kind of wondering what other
I
people
love it.
Okay,
love
so
Pineapple electronics. I want to make a circuit out of pineapples.
So this is one of there we are, Bathsheba's pieces. So this is made out of sintered metal, and it's mathematically complicated, right?
Whoa.
It's just really beautiful, super satisfying to hold, and absolutely gorgeous. So we saw her work at the very first Maker Faire back in 2006, and we're just smitten. And so that's when we started working on the Candy Fab project, making a 3D printer that worked with sugar as the printing media. So that got me not so much into electronics as into mechanisms. Because we did things like the Z stage for the original Candy Fab. So the vertical motion system for that was made out of a car jack that we had turned into a servo motor.
Wow.
To lift a large volume of sugar up and down, plus the wooden bucket that held it essentially. So it needed to be able to lift a lot of material very precisely. The types of mechanisms that we used for that were all fun and repurposed and interesting. We actually used pen plotters for a lot of it, because you could get the old HP pen plotters at the surplus stores for next to nothing, and they have, linear shafts and motion control stages that are of wonderful quality. And so we did a lot of repurposing. As we moved forward with the project, we started trying to recreate those types of designs and build something that was manufacturable from scratch, which is a lot harder in some ways. But you can't, it's very hard to give someone instructions to make something from, I found this at a surplus store.
Yeah.
Yes.
Pretty sure it works like this. But...
so you need a model. No. Yeah.
I just totally thought of an engineering use for pen plotters, which I have actually done before, which is you can use them to plot circuit boards on copper clad substrate and etch your own circuit boards with them.
Yeah, so that is something that people have done with AxiDraw. The other way that you can do that is actually with a conductive pen. You can just draw your circuit instead of etching it, and so people have done that with AxiDraw and with Eggbot as well.
Nice.
If you need a spherical circuit.
If you need a conductive egg,
yes,
got you
Was
covered.
it way easier going from Eggbot to pen plotter that just has two axes?
No, because the Eggbot is essentially direct drive. So you have a motor that's turning the egg, right?
Yeah.
And you have a motor that's just turning the pen, just moving it in an arc over the egg.
Mm-hmm.
There's no intermediary hardware, or very little. For the pen, there's a servo motor that just lifts and lowers. So
is it spring kind of loaded to keep touch with the surface of the egg, or
no? It's gravity driven. So it's lifted away from the egg and then lowered to just right along the surface of gravity.
Got it.
And that's that's true with the AxiDraw as well. The watercolor bot had powered down. It would press the brush down because you need to be able to push the brush onto the paper. But the AxiDraw and the Eggbot were both just gravity driven.
Nice.
So no, all of the other types of motion control that we've done are more complicated because you need some kind of hardware to translate it into those positions. The AxiDraw does not have any moving motors. Neither did the watercolor bot. So the watercolor bot used an Etch-a-Sketch style motion system with essentially cords that pulled the stages around.
Nice.
And the AxiDraw uses a single belt that's connected to to two motors. And so neither of those is specifically X or Y. It's a combination of them that drives it to the correct location. So those are much more complicated than the Eggbot, which is just a direct. We have
Fair
rotation and we have pen, and that's it.
Rotation, pen, gravity. Love it.
Yeah.
So Lee, you're getting a ton of love for your pineapple switches and whole series of switches.
Oh yeah, I mean, anyone who follows me on Twitter knows I love a good switch.
Dan says it's your fault that every time he eats a bowl of cereal, he thinks of it as a switch.
Excellent. That's
Nice.
so good to hear.
I love that.
I've seen a lot of projects with things like clips for switches because they return to a closed position, so you can decide is your switch on this end where you're actively doing it, or is it on this end where it's going to be closed all the time? And then of course good old binder clips are also super useful for those kinds of explorations with electronics. One of the electronics projects that we did that was sort of foundational for me was the BristleBot, which is a vibrating motor on the head of a toothbrush.
Oh yeah. Yeah. I'm very familiar with this circuit as well.
When we first released the video for that and the project for that, it just went like wildfire. It's had millions and millions and millions of views, and people don't even know that we're the ones who did it anymore.
I actually had no idea that it was you who did that, and I use that circuit again all the time in teaching. So thank you so much.
As you should, right? That's what we want to have happen. Is we want for these learning tools to get out there to people to use.
Mm-hmm.
So I'm happy to hear that you use it. And yeah, we've seen it in so many educational circumstances. We took it to Maker Faire one time, and we just set out a pile of components and a table with a rim around the edge and some really rudimentary instructions. And we put out a donation can for people. We said suggested donation $2 or something like that. And that was like barely covering the cost of materials, but we're like, okay, that's fine. And we would look over and we'd see people doing just amazing things. We saw a little, like maybe 4-year-old with the bolt cutters to cut the head off of the toothbrush. And her dad's kind of looking and holding the toothbrush, and it's just wonderful.
That's awesome.
So at one point, someone comes over to me, very, very concerned. He says, "I have a problem. I can't fit my money into your donation can." Because I hadn't been paying any attention to that, and we'd brought too many projects to Maker Faire, so we weren't paying very close attention to the table. And so I take the can and I take the lid off, and it's just filled with crumpled $1 bills, and I'm like shaking it out into my bag, trying to get all the dollar bills out and quarters, and it was great. It was hilarious.
Awesome. That is
actually
awesome.
Another project that I know that that you folks did that I had no idea that you told me about was the All Yarns Are Beautiful project.
Yeah, we worked
one of my favorites.
Worked with them for a while. That's a really interesting project in its scope and difficulty from so many different directions. We helped create a version of the board for them, and we manufactured it and shipped it out. And helped with the software for a while. It is really difficult to know with a project like that where you're doing an interface for vintage hardware. So this is a project where you're taking these vintage knitting machines and putting modern controller board on it so that you can connect it to your computer and have it knit the image that you've created.
Nice.
So
I hope you're still watching. This is relevant to your interests.
So the old ways of doing it using the vintage hardware involved things like punch cards, Mylar sheets, the pre-programmed designs, pressing buttons. There was one that you could hook it up to your TV and toggle pixels.
Yes.
There was all kinds of different ways of doing it, but they were very tedious. And so the idea was, okay, let's just connect it to your computer. But there's so many levels to this project. You have to have a working knitting machine.
Yeah.
You don't necessarily need the electronics to be working, but the knitting machine itself needs to work. You need to know that the person who is using the knitting machine knows how to use the knitting machine. Mm-hmm. You need to know that the hardware works. You need to know that the software works, and it's an open source project, and the software has issues, and they're doing a good job of developing it, but it's an off and on project. That's a project, a love project, not a profit project. And so there's a lot of challenge to a project like that. And we stopped producing the hardware. It's an open source hardware project as well. So we've published the designs, and other people are now taking up some of the manufacturing on that. But I'm kind of glad that we stopped manufacturing it when we did. If we were trying to manufacture it now, during this chip shortage and everything, we couldn't even get the connectors because they're vintage connectors for this
Right.
stuff.
Oh, wow,
You know, so you
yeah.
had to go, you had to jump hoops to get all of the connectors to connect all of the old solenoids that drive the needles on the knitting machines. So I can't imagine what it's like now. It's got to be just that much harder to do. But yes, we helped out with that project for a while, and there's quite a bit of our hardware out there running knitting machines, which is a really satisfying thing.
Nice.
I also think that like a lot of those projects are really interesting ways for people to get into electronics. Like it's like such an interesting overlap. I'm on like a couple of those like, you know, generative knitting communities that are similar to Plot or Twitter, but for knitting. And the mix of people that are on there is like always like kind of mind blowing and super interesting.
We have a working op amp here.
Oh, great.
Amazing.
Yeah.
So did you do the follower circuit?
So I've done the follower circuit. So what I have going on here, kind of off camera, I have two power supplies, two like benchtop power supplies. They're both set to 15 volts. Ground of one is hooked into positive of the other. So essentially we're creating positive and negative 15 volts for our power supply here. And so we have positive 15 volts going in on red here, and then negative 15 volts going in on black. So that's the power to our op amp. And then our output is connected to the inverting input, so the negative input. And then we're putting in a signal on the positive input, the non-inverting input. And so there are a couple of like rules of op amps. You can kind of, so you can think of op amps as an integrated circuit black box if you want to, right? But I will also say though that Lenore, that the PDF that is on your website that goes into all of the stages and what each of the transistors do is amazing. I'm like still working my way through it because I'm just unable to skim it. I need to like understand what's going on.
It's a deep dive.
Yeah, it's a really deep dive, and it's really, really wonderful.
I was going to read through it before tonight, and I just didn't have the time to because there's so much information in it.
There is. I might have actually kind of fallen asleep last night reading it because I was like, oh, I'll give this a quick thing, and then like 2 hours later, I was still like, whoa, this is amazing.
So that level of detail comes from the collaboration between Eric and Wenzel,
Nice.
my partner. That the two of them are great at extracting all of the information about a subject and then making it understandable. That there's a depth of knowledge and then an ability to convey it, and the two of them are really good at that.
Yeah, it's amazing, and it's meaty, but it's like it's broken down super well. So one thing, oh my gosh, like I wish I had learned this. The mnemonic for NPN and PNP. I might actually be able to draw a transistor properly without actually having to look it up. For whatever reason, my brain never wants to remember like which way is which. And I know this is like shameful for somebody who's been working in electronics for like 20 years or whatever, but like seriously, I just like it's there and then it leaves my brain. So it was like, now I need to remember the mnemonic, right?
It was mnemonic. I'm dying to know.
The NP was like, wait. Not okay. So there's NPNs. It's like it was like not pointing in, right? I think was that. I'm gonna have to look it up right now. Step 1, remember the mnemonic. Step 2, then remember how the circuit goes. And then it was like not like so it was like not pointing in and like perfectly in pointing or something like that. Shoot, I'm totally gonna have to cheat and look at your website now. Totally, because now it's driving me crazy. Obviously, I need, I need like notes and a teleprompter for this stuff.
So all of these disintegrated circuit kits and projects are collaboration between us and Eric. So he's done the circuit design and, like I said, a lot of the deep dive knowledge, and we do production and art direction, and then the communication side of it. But definitely a deep collaboration there between us. It's been awesome.
Nice. So, where is it? We're here. Transistors. Okay, here we go. Yeah. Shoot, where is it? Oh, here we go. Okay. Yes. Okay. Pointing in, please, and not pointing in. So I got the not pointing in properly. It's correct, but the PNP was pointing in, please. NPN is not pointing in, and it refers to the direction that the arrows go when you draw a transistor symbol. So like when you're designing a circuit, you draw a schematic for it, which is this circuit that is basically completely represented by symbols. It's just a illustrative. It's basically illustrative of the signal flow throughout your circuit. And so, resistors have a certain symbol. They're like these squigglies with sharp points, and then like inductors are squigglies with rounded points, and capacitors are like two plates next to each other. And so when you start designing circuits and reading circuits and things like that, then you can understand visually a little bit better reading a schematic what's going on with the whole signal flow. And so there are two types of transistors. One is controlled by pulling current out of it. One is controlled by putting current into it. So they're just like opposites of each other. And basically, like the only difference in the schematic symbol is that one has like an arrow pointing out of it and one has an arrow pointing into it. And it's just one of those things that is difficult for me to remember which is which. So it's like, NPN, pointing in, and PNP. NPN not pointing in, PNP pointing in, please. I like the please in there too. It's so polite. But yeah, so op amps, they're like, you can treat them as black boxes. You can solder this together and be like, okay, this was super fun, but I don't really care how the circuit inside works. Just tell me like how I can use an op amp, and that's fine too. And so op amps, you apply power to them. They have these two inputs and they have one output. And they're typically used when you feed the output back to one of the inputs. And what the op amp tries to do is it tries to vary that output so that both of the inputs are at the same voltage. And that is like the basic principle of operation of an op amp. And like with that rule, you can add a bunch of different surrounding circuitry that make it do all the different things that we were talking about, like amplifying or offsetting or whatever, or comparing. Comparing is actually the easiest one. It's you just don't do any surrounding circuitry to it, and it will either be swing positive if the one is bigger than the other, or swing negative if it's not. But what I've done here is made what's called a voltage follower circuit. And so basically you just connect the output directly to one of the inputs, and so it will try to vary the output to match this other input. So right now I have 7.5 volts coming in on this input, and what I should see is 7.5 volts on the output, because it's trying to make these two voltages, basically equal. Or if you want to get really technical about it, it's trying to make the difference between them 0. Same way of saying it. So right now, I can get as many things as I can in this little view here. So I'm probing this with respect to actual ground, which is, I had to remember that for a second. black is not ground on this. Black is like negative 15 volts. So we can see that my input voltage here is 7.5 volts. And my output voltage here is also 7.5 volts, which is exactly what we should expect. Yay! And like you might be like, well, what good is that circuit? Like, couldn't you just, it's just doing this, it's putting out the same thing that you put in. Couldn't you just like get rid of the op amp, right? Like, what's it even good for? This kind of circuit is actually very, very useful for a lot of things. Because the other thing about op amps is that they're essentially like little sniffers. They will tell you information about what's present at that point of the circuit without actually without altering the circuit. So they pull practically no current for into the inputs, and so they really don't alter the signal that they're attached to. And that is super handy because let's take our audio signal example again. You might have maybe, I don't know, people have tried to perhaps like take an audio output and split it into two sets of headphones, right? Mm-hmm. And what you might notice is that you get kind of crappy audio that's like sort of at very low volume in both of those, right? And that's basically because you are now, your headphones consume power, and you're now trying to drive two things with that audio signal instead of just the one thing that it's supposed to drive. And so this kind of circuit is also called a buffer. And what happens is the op amp basically like sniffs that input and says like, okay, we're going to generate an output that's exactly like the input, but I'm going to supply all of this extra current. I'm not going to try to like pull it out of your originating signal. And so what that means is that your output now, you could hook up like two different buffers and have like two different audio outputs that now are at proper volume and that are a faithful reproduction of your original audio signal. So yeah. So so this circuit, even though it seems like kind of super simple and like useless, is actually quite useful and used in a lot of different applications.
So we used this circuit actually to test how well our 741 was working, because we wanted to know is this working as well as an IC would be, and it turns out it's really quite good. As you see, the follower, you're pretty darn close. Yeah. And we think it's just because modern transistors are really consistent. So we're not doing any matching of transistors or anything. We just get them out of a box of bulk transistors. And we're still getting really good results, even though it's not all on the same die like it would be in a chip. And it's just because modern production is so uniform.
Nice. Yeah, I'm impressed by that as well, because I would have thought you would have had to have some matched pairs here and there in order to not have like tiny little errors that then add up and then would produce like an offset in your voltage. So like, I would have maybe assumed if I put 7.49 volts in, maybe I would have gotten like 7.52 volts out or something like that, which, may not be a big deal, or it might be a huge deal depending upon what you're doing with that. So that is impressive, because also like buying matched pairs of things are way more expensive than just buying individual ones. So yeah.
The trick about getting precision resistors out of bulk resistors?
No, tell me what I know like a little bit, but tell me what you're thinking.
So if you have ones that are 5%, what that means is that they've taken all the ones that were 1% out of that batch and left all the ones that are 5%, which means you're going to have about half that are over and about half that are under.
Yeah.
So you want to pick a value that's about 3% off from the value that you want, and then just bin it in two.
Nice.
And about half of them will work well for you, and about half of them won't.
Half of them won't. Nice. Nice. Of course, there's not a whole lot of price difference these days, at least between 1%ers and 5% for our stuff.
Sure,
I mean, if you're making millions and millions of things, then saving a few cents per resistor will totally make a difference. But yeah. So what I'm going to try to do in the background here is, so this is like this is like table of solder kits right now. So I have this like function generator kit that got ages ago, and I have like this oscilloscope kit that we just finished soldering up the other day. And what I'm going to attempt to do right now is do a simple amplifier circuit, kind of like the volume knob thing that I've been talking about. And we're going to produce a sine wave with the function generator and put it into our 741. And we'll have a little circuit. This is just a resistor rotary pot. So I have 15 volts going across it, and right now it's in the middle and it's spitting out 7.5. But we'll hook that up, and so we'll be able to basically vary the knob and hopefully like see the signal grow and shrink. That's the idea. We'll see how well we've done with all of these kits. But yeah, let's see. So that's our little oscilloscope kit. I am totally going to cheat and get my paper for the for a non-inverting amplifier circuit. So we were talking about schematic symbols before. This is the schematic symbol for an op amp. You basically have your non-inverting input, your inverting input, and your output.
Nice.
Yeah, and you don't, and you generally don't draw the power pins because they're sort of assumed and extraneous. So, yes. So our two resistors are basically our potentiometer here. So, all right. So now we're going to hook up. I'm going to unpower my amplifier first.
Lenore, do you want to tell us about this jacket? Is it just like a cool jacket that you have, or can other people get this?
No, it's totally a cool jacket. This is the Electro Cuties jacket.
Oh yes.
So this is by Sailor Mercury. And it was a one time. I don't know if she has any more on her store. Her most recent pre-order of jackets was for the Art Makers Heartbreakers.
Yeah, I saw that
jacket.
So
so she does batch runs of fabulous design clothing, sweatshirts and jackets and things. And she did this one. I was like, that I have to have.
That is super awesome. All right, so let's see. I'm going to do that and put that in the end. This guy's going to the output. Oh, I need like longer wires, I think. That's those. All right. So I'm just going to disconnect that for right now. And this guy is going to our output. So Brittany was still watching and says that her mind was blown with the knitting machine idea. Yes, getting more knitters. I love it.
Yeah, we've got to convert all the crafters into hackers.
Yeah. I'm working on it. I really am.
I mean, many of the crafters are hackers in their own right, just in different sets of materials. That,
absolutely.
It's fascinating to see what they do. And by they, I mean us, since I would consider myself one.
Yeah,
for sure.
Absolutely. Absolutely.
I love all the intersections of materials. One of my favorites actually is papercraft and electronics. So stuff like the Chibitronics circuits, and a long time ago I did a electric origami project. So putting circuitry onto the paper that you then fold up that then creates a circuit.
Oh, that's super cool.
Cool.
Super fun, yeah.
Very, very cool. Okay, I think one more.
Is that using like conductive pens?
I did it in a couple of manners, and it was primarily using aluminum foil, actually. I did a toner as glue method where you iron the aluminum foil onto the toner that you printed onto a piece of paper. So that was one method. And the other one was ironing it onto adhesive paper, like photo...
Like heat bond?
Like photo transfer paper, those kinds of things. So... yeah, just tried a few different things. Or the easy way now we realize is just cut it out of aluminum tape that you find in the plumbing section at the hardware store. Either copper, you find the copper tape is in the roofing section and the aluminum tape is in the plumbing section. Because you
for the plumbing, I didn't realize that roofers used copper tape.
I think for flashing and so on. I believe that's why you find it there. But yeah, it's because in a hardware store you can't possibly put things in order by shape and so on. You have to put it by what it's used for. You can't put all the adhesives together.
That would be silly.
I would love to see a hardware store organized by shape. I think that would be so much fun.
That would be the best. Yes. That would be great. All of the tubes are here. It doesn't matter if they're dryer tubes, or plumbing tubes, or electrical conduit tubes. All the tubes in one place.
I like it.
Yeah.
All right. Let's see. I think I'm almost done here. That one out to here. This one out to this one. Oh, this is a spaghetti mess. Oh my gosh, we have a sine wave on the oscilloscope. It's amazing. Let's see if I can get this in the frame a little bit better without getting it all. Yes, the polarizer too. I was testing this out. I'm like, gosh, I guess the camera isn't picking up this LCD screen. It's all black. And then I remembered that there was like a polarizer on the camera and I had the LCD screen tilted at 90. And I was like, oh no, it's all working exactly as it should. Yeah. So, all right, I'm going to try, I think, I don't really need to see the waveform generator. It's not very interesting. Okay. Let's see about if I can get this in. All right, nothing's shorting out. All right, that's good. So, yeah, do this way. There we go.
There it is.
Yeah, so now here's the test. Let me turn the knob. Oh, there we go. Awesome. We've made an op amp be an amplifier. So I'm basically changing the knob, just, dialing the knob back and forth. It is set up backwards from a normal volume knob. I'm turning counterclockwise to increase the volume right now. We'll have to work on the UI here. But yeah, there we go. We've set up our circuit and it's all working. That's so exciting.
Nice.
Cool. So yeah, we're just feeding this. We're just feeding that sine wave in. What we're seeing, let's see, we're on 2 volts per division. It's a 5 volt sine wave, so it's normally like right around that level. And so we can, make it go probably pretty high. It'll start clipping at some point since we're putting in a 0 to 5 volt sine wave. If I was so we're only going to be able to amplify it so much before we hit that 15 volt limit at the top rail. If I made it centered around 0 volts, we'd be able to amplify it a little bit more to both positive and negative 15. So yeah, but there we go.
Nice.
Yay. Oh yeah. So Bob's saying if I swap the legs of the resistor, will it work the way I want? It will, except that then I wouldn't be able to actually twiddle the knob because it would be pointing the wrong direction. I could also swap like which one's the input and which one's the output, but I'm gonna call it good for right now. I'm gonna call that Rev 1 done. For next iteration is swap the
proof of concept.
Exactly. No, that's awesome. So yeah, I might be able to explain what's going on here a little bit. It's not the prettiest, but it works, which is great. So yes, let's see if I can also get our op amp symbol in here. So our V in is our signal from the waveform generator. So that's coming in to the positive input right here. And then this resistor network is basically our knob right here. It's our and so we're actually like varying these two values of resistors when we twist the knob. So the midpoint is hooked up to the inverting, which is this guy. So you can see middle going to that guy. And then it's our, okay, yes. And then our output is hooked up to the top of our two resistors here. So the top of the knob, and then the bottom of the knob is hooked up to ground, which is going to our midpoint of our power supplies. And then positive 15 and negative 15 again. And everything else is also hooked up to ground. Our oscilloscope has a ground reference that's sharing with that that's sharing with the resistor, the bottom part of the knob. Our waveform generator ground reference is also sharing with the knob. And ground is just 0 volts for people who are not electrical people who are watching. So, and then we're probing our oscilloscope at this output point here, which is the same as the top there. So it's not too terribly complex, although it looks like it from any good spaghetti prototyping mess. Yeah. Cool. Oh, Brown Dog Gadgets makes some nice conductive tape. Good to know.
Mm-hmm.
Good to know. And David's also down for some generative knitting. Yeah.
The Chibitronics conductive tape is nice, narrow stuff, but you really can just buy it from the hardware store.
Cool.
And then you can cut it into fancy shapes.
Yes. Cool. Well, awesome. Well, is there anything else that is going on at Evil Mad Scientist that we should know about or be looking for in the future once we can get parts?
So we're primarily focused on AxiDraw production right now, and just making pen plotters all the time. Nice. Working on software updates for that, and eventually maybe some hardware updates and new things down the road, but they'll probably be waiting until supply chains settle down a little bit.
Makes sense.
Totally. Awesome. Well, I think this was a successful solder sesh.
Mhm.
Two successful circuits, so that's awesome.
Yeah,
And then you've got lots of reading material for your op amp research.
definitely, definitely. And yes, yes. But now I actually have the circuit here in front of me, so I could actually probe those different spots on the circuit and even get a better understanding, which is kind of cool. So yeah, I'm excited to do a little bit of that.
Okay, so you said you didn't do higher electronics in your undergrad. Or in your college? What did you do?
Engineering. So I went to Harvey Mudd, and we graduate with general engineering degrees there. So we're required to take a smattering of courses in a whole bunch of different disciplines: electronics, mechanics, chemical. There was like a tiny bit of computer engineering as well in that. Some stuff that I'm sure I'm forgetting, but we basically had only 3 electives that we could kind of do whatever we wanted with. And so I didn't have a good experience in the intro to electrical engineering class. The professor taught from the book, and there was no lab component to the class, so we never made any projects. So it seemed all very esoteric. And if all you're learning about op amps is from a book, if you're not soldering something together and putting signals in and twiddling knobs and seeing what happens, it's just kind of all like, who cares, And so I wasn't interested in it, and I did really badly in it. So I did mostly kind of manufacturing-ish electives. There was one class, manufacturing and metallurgy, and like the final project was to make 10 of something. And all I need is a bead blaster, and I will finish that project like 25, 30 years later.
Oh, so one of the little bright spots this week for us is that I can tell that school is back in session because the students are buying their 741 kits right now.
Nice.
So there are a couple of universities that use them in some of their classes, and I'm like, oh, goody, they're getting to get their hands
That's a nice
dirty.
feeling, I'm sure.
Yeah, this kind of stuff is so awesome. Like if I had stuff like this when I was a student, it would have made a huge difference for me.
Right.
I am definitely a project-based learner. And I didn't really even understand that about myself until I started working. Like I was good at school from a general standpoint. I was like good at school, but I didn't necessarily always retain a lot of information. And I would take a class, and then a few years later, if I didn't do anything with that knowledge, with that instruction, it would just be like, oh yeah, I think I did something about that, whatever. So yeah, it wasn't until I started working and actually like solving problems, and that's when I first started working with electronics and designing with electronics. And that was a whole like big snafu of funding restructure, and the job that I got hired for didn't really exist anymore. And so like they were like, okay, well, we have funding for this other project that needs like an intro kind of electrical engineer, and she's taken some courses. She can solder jewelry. I'm sure we can teach her how to solder electronics.
Nice.
And that was basically how I started out. And all of the practical stuff that I've learned, and a lot of the higher level stuff that I've learned, how to design circuit boards, how to really like draw and read schematics, all that stuff I learned on the job from there on out. So yeah, it made a huge difference, because all of a sudden we had this like problem that we were trying to solve. We had this like small little airplane that we were trying to make fly, and we're trying to figure out how many feet off the ground it was. So there we go. That was like my introduction to pressure sensors, and suddenly it was a lot more interesting than it was when I was just learning about stuff from a book. Yeah.
Awesome.
Yeah. Cool. Well, I think I'm just gonna kind of wrap it up there. Thanks, like everybody, for joining. Thank you so much, Lenore. Yay! Thank you for coming on. And
Thank you for
adding
having me. This has been
everything.
fun.
Good. Yay! I'm glad. Well, yeah, we'll definitely have to do this again, like, in like 6 months to a year or something, when there's like more new stuff to talk about. And yeah,
Excellent.
cool. And thank you everybody for joining and putting your comments and stuff in the chat. I hope that we got to everything. I think we have done. We have gotten to all of the questions, I think. But if not, definitely comment on YouTube, and we will answer questions that way, because we do monitor the comments. And thank you, Lee, so much for
Yeah, this was so
keeping
much
stuff
fun.
moving and flowing. Yeah, cool. All right. Catch you all next week.
Bye.
Bye.